Alright, hello. Today we're going to have a look at integrating using more complicated trigonometric functions. So we've seen some trigonometric and inverse trigonometric results already in integration. And in this lesson we're going to focus on powers of trig functions. Now, powers of trigonometric integrals requires the use of Pythagorean identities, most importantly sine squared x plus cos squared x equals 1, and also standard integrals. We will have trig functions raised to a single power, raised to a power, singly or in pairs, and there's many different approaches depending on the function and their power. Some important things to note that we have already memorised and done in Extension 1 and in Advanced are those couple of identities there. So, example number 1, we're going to have a look at the integral of sine cubed of x dx. So, the integral of sine cubed, unfortunately, it's not in any of the forms that we have seen here. But we might want to remind ourselves and go, okay, sine cubed of x, well, that simply is the integral of sine squared of x times by sine of x dx. Now, we know the integral of sine squared of x is half cos 2x. We also know that sine squared of x is 1 minus cos squared of x. So those two things potentially could be useful to us, and we're going to consider them here. If we go that, okay, we've got sine squared of x, the integral is a half 1 minus cos 2x. Potentially not going to be that useful because I do know how to integrate 1 minus cos of 2x, but I don't necessarily know how to integrate cos of 2x times sine of x. So I'm thinking the identity sine squared of x is 1 minus cos squared of x might be a bit more useful here. So sine squared of x, it's going to equal sine of x times by 1 minus cos squared of x dx. If we expand that, we get the integral of sine of x minus sine of x cos squared of x dx. And we're going to use a u substitution for the second bit. So I'm going to evaluate the first integral, which is minus cos of x minus the integral of sine of x cos squared of x. And that's a good strategy that I like to use in an exam. Let's just do something that's easier and we'll do this separately. Let's move up to here. So we've got the integral of sine of x cos squared of x. I'm going to let u equal cos of x, which means du is equal to sine of x dx. Nice and easy because we can replace sine of x dx with du. So this is now the integral of u squared du. Now that's equal to u cubed on 3, which is cos cubed x on 3. So this final integral is minus cos x minus the integral, minus cos cubed x on 3 plus c. Awesome. Okay, the next integral we're going to have a look at is tan to the power of 4 of x. And some important integrals that we're going to note. First of all, tan squared x plus 1 is sec squared x. And then there's some important integrals down there that might be useful in memorising. You can derive all of these, but it's much easier just to memorise them. So we've got the integral of tan to the power of 4x. Now we don't know how to integrate tan to the power of 4x, but we do know it's tan squared of x times by tan squared of x, and I do know how to integrate tan squared of x. So why don't I say that this is... So I don't know how to integrate tan squared of x, but I do know how to integrate sec squared of x. So why don't we write this as tan squared of x multiplied by sec squared x minus 1. And that's using this identity up here. Tan squared of x is sec squared of x minus 1. Okay. So we're going to expand that now. So this is tan squared of x sec squared of x minus tan squared of x. dx, and of course we're still integrating. Now, we don't know how to integrate tan squared of x, but I can again integrate sec squared of x, and tan squared of x, sec squared of x, it looks quite scary to integrate, but if we differentiate tan of x, we get sec squared of x. So I might, first of all, we might evaluate this bit first. Let's do this part of the integral first. So let's integrate tan squared of x, sec squared of x. You're allowed to do things separately. As you get better at these, you'll be able to just integrate this without a u substitution, but you can just do things separately and combine it at the end. So let's u equal tan of x. I'm not letting it equal tan squared of x because I don't necessarily know how to differentiate tan of x tan squared of x as easy as I do tan squared of x, or tan of x, sorry. I said that all wrong, but you get what I mean. Equals sec squared of x dx. So we've got a dx here at the end, so we can just replace sec squared of x dx with du. So this is the integral of u squared du, which is u cubed on 3 plus c. Now u is tan of x, so this is tan cubed of x on 3. We'll do the plus c at the end, but we do know it's there. Now tan squared of x, I might do some rubbing out. I'm going to put this over here. I'm going to write an equals sign here, and I'm going to rub all this out. Let's do the integral of tan squared of x. Well, I know that that's equal to sec squared x minus 1. And the integral of sec squared x is tan x and minus x. So we've got that this integral is equal to tan cubed of x minus tan of x plus x, so we're carrying through that minus into here, and then we're plussing c, and we're done. Okay, next example. We have to prove that the integral of sec x is equal to ln of tan x plus sec x. Again, this question can be quite tricky, especially if we were not given this. You can be asked this, which is why it's important just to memorize this specific identity. And I showed you in a previous video, in the first video of this topic, that triangle mnemonic that I found in Steve Howard's textbook. So the process of doing this is we're going to times by tan x plus sec x on tan x plus sec x. So we're going to get sec x, and we're going to multiply it by tan x plus sec x on tan x. And we're allowed to do that because tan x plus sec x is just 1. And if we might recall from one of the Cambridge textbook exercises in Extension 1 that this was actually a question. So if we simplify the top, it's going to be sec x tan x plus sec squared x on tan x plus sec x. Now, again, this looks scary, but it's not. Because if we differentiate tan of x, we get sec squared of x. And if we differentiate sec of x, we should recall that we get sec x tan of x. So this is simply ln of tan x plus sec x plus c, which is what we're required to prove. So we're done. Example number 4, we're looking at the integral of tan cubed x sec of x. Now, we don't necessarily know how to integrate sec of x or tan cubed of x, so there's a problem with this question. However, I do know I can integrate sec squared of x, and I can integrate tan squared of x knowing that the identity of 1 plus tan squared of x is sec squared of x. So we're going to split up this question and say this is the integral of tan of x times tan squared of x times sec of x. And I know that I can actually get sec squared of x from tan squared of x. So I can say this is the integral of tan of x, sec of x, and then it's going to be sec squared of x minus 1 dx. So if we expand that, we're going to get the integral tan x sec x sec squared of x minus tan x sec x dx. Now that's actually very, very easy to integrate. We're going to do the first part of the integral using the reverse chain rule. So sec squared of x, well, if you differentiate sec of x, you actually get tan of x sec of x. So the differentiation, if we wrote it like this, the differentiation is actually outside the brackets. So we can just say this is sec of x cubed on 3 minus, well, the integral of tan x sec of x is actually sec of x. And that's because the differentiation of sec of x is tan x sec of x. And you can prove that just using normal rules of differentiation with the fact that tan is sine on cos and sec is 1 on cos and things like that. Okay, the next example. We're looking at the integral of sine of 2x plus sine of 4x squared. This question looks scary, but it's not. The thing that makes it look scary is the squared. But we can deal with that because let's just get rid of the squared and expand it. So this is just the integral of sine squared, what did I write, sec? Sine squared of 2x plus, I might write sine squared 4x plus 2 lots of sine 2x sine 4x. Now I'm thinking my compound and product to sum formula for that last bit of the integral, but for the first bit we're just going to use those extension 1 identities. The fact that this is the integral of a half times by 1 minus cos of 2x, so cos of 4x in this case, because 2x times 2 is 4x, plus a half outside 1 minus cos of 8x in this instance. And that's because of this identity from the beginning of this lesson, that the integral of sine squared of x is 1 minus cos of 2x. So we're just multiplying that number by 2, so we get 4 and 8 respectively. In the last bit, we're thinking our product to sum identity. So the product to sum identity, if you've got two signs, tells us that this is going to be plus. If you've got a 2 here, it's going to be cos of 4x minus 2x. I think it might be better to write the larger one first because that will come in, that will make our identity, it will fit with the identity if a is bigger. So it's going to be the minusing them first, which is cos of 4x minus cos of 2x, or 4x minus 2x, which is 2x. And then we're taking away them added together, so cos of 6x. The reason I wrote this one first now is because if you subtracted 2x minus 4x, you would get minus 2x here, which we don't like. And now this is very easy to integrate now. If we have a go at expanding and simplifying that, you're just going to get 1 minus a half cos of 4x plus cos of 2x minus cos of 6x minus a half cos of 8x. So I've just rewritten that in a different form by expanding and simplifying. The 1 comes from a half plus a half. And we're integrating that, put a dx on the end, and very easy to integrate. That's just going to be x minus sine of, I'm going to write them in order, so 8x on 16 minus sine 4x on 8 minus sine 6x on 6 plus sine of 2x on 2 plus c. Alright, and that's the first lot of trigonometric integrals. Thanks for listening.